So in this chapter, we'll be covering gases, and we'll be covering more specifically properties of gases and calculations that deal with gases that describe not only the gases but the environment that they are in. So earlier on in the class, we discussed the differences between metals and nonmetals. And so many of the nonmetals are found to be gases in the natural environment. And so specifically, we're discussing noble gases, which are found in group 8 or 18. Um, Many of the diatomics of the uh, nonmetals in the periodic table, including hydrogen, nitrogen, oxygen, fluorine, and chlorine, and some of the oxides that are created by covalent bonding through nonmetals, such as carbon dioxide and nitrous dioxide and things like that. There are many concerns over gases, including environmental and health concerns. As far as the environment is concerned, we have greenhouse gases, which are responsible for global warming. And gases that are included in those groupings are things like methane or things like carbon dioxide, which can contribute to global warming. Things like chlorofluorocarbons or CFCs, which are responsible for destroying the ozone layer. And then we can have health concerns over some of these organic compounds that are found to be in the gas phase, and things like gases that are found in the example I give here, paint thinners and other what we call volatile organic compounds or VOCs, and even things like carbon monoxide. And we know carbon monoxide is a poisonous gas that is odorless, and we need to know concentrations of those to make sure that people are safe. So we, gases are have special properties to them, and many of those special properties are included in the kinetic theory of gases. Um, Gases are a phase of matter that have their particles move at very high velocities, or they move very fast. They are also very spread apart. The gas molecules are and gas particles are very have a lot of distance between each other, and so there's a lot of empty space between the gas particles. Part of the reason for that is because they really have no attractive force toward each other. Um, we also described phases of matter in terms of definite volume and definite shape. Gases don't have a definite volume or definite shape. Gases can change their volumes and change their shapes depending on what container they're being held in. Gases are always in constant motion, they're always moving around, and um, their kinetic energies increase with increases in temperature. So uh, the higher the temperature, the faster these gas molecules are going to move around. And so other properties of gases are dependent on those kinetic energies. We describe gases in terms of four properties. One is pressure, two is volume, three is temperature, and four is the amount. And so we have special units that are attributed to each of these different properties. Pressure is measured in usually in atmospheres or millimeters of mercury, but can also be found in terms of torr and pascals. The ones that we'll be most concerned with in this course is atmospheres and millimeters of mercury. And pressure is defined as the force exerted to the walls of its container. So the force is determined by how fast these molecules are moving around and how much of the gas you have. Volume is typically measured in liters, milliliters, and cubic meters. The one that we'll probably use most is liters, but you may see the other ones. And volume is just the amount of space that the gas takes up. Um, Temperature, it will be using the units of Celsius and Kelvin, and we are going to perform calculations using these temperatures. And so the unit that you will have to be using is Kelvin in your calculation. So even though a problem may include degrees Celsius, you probably have to convert those degrees Celsius to Kelvin. And so temperature is just a measurement of the amount of kinetic energy that the gas molecules have. And then we also have the amount. And the amount of the gases can be measured in grams or moles. And the unit that we'll be using in calculations will be in moles. So when we perform calculations, you may have to convert the grams into moles. And the amount is just how much of the gas you have. So we'll be looking at pressure since we haven't really talked about pressure too much in detail. So we'll be going over what pressure is and calculations involving pressure and the units of pressure in detail in this next section. So pressure is just the amount of force acting on a specific area. So we're not going to have to perform any calculations using that first equation, which is force divided by area equal to pressure. But pressure is just the amount of force that these particles have in a certain area. So we said before, these gases are going to be moving a lot and moving very fast, and they'll be contained in some type of container or in a room. And so these gas molecules are going to be bouncing off the walls of whatever container they're being held in. And so the amount of force that these gas molecules have in a specific area of that container is the pressure. We usually have our units of pressure in atmospheres, and 1 atmosphere is basically the pressure, the normal pressure of our atmosphere acting on Earth, and so it's just a standardized unit that we use. And we have some conversions here of converting 1 atmosphere to other units. The first one is probably the most specific, or I should say the one most commonly used and the one that's going to be most used in this class. And that will be 1 atmosphere is equal to 760 millimeters of mercury. You're not going to be asked to memorize that. That will be given to you. So just be aware of that. The second one is another common one that we won't use nearly as much, but 1 atmosphere is equal to 760 torr. And then we have a couple other conversions, but we won't really be too concerned with those. So we'll have a quick learning check of how to convert from one unit to the other. And so this first question is asking, what is 475 millimeters of mercury expressed in atmospheres? And so in order to solve a problem like this, you have to set up a conversion factor, which we have done previously in the past units. And so you just want to set up a ratio. And so we want to use that conversion factor that 1 atmosphere is equal to 760 millimeters of mercury. So you want to basically divide 475 millimeters of mercury by 760 to solve for that answer. And we would get choice B in this case. Number 2 is asking a similar question, just in the opposite direction. Number 2 is asking to solve for the pressure in a tire that it has 2 atmosphere of pressure, and is asking what would be the pressure in units of millimeters of mercury. So we're going to use the same conversion factor, just flipped over. So we would, in this case, want to multiply our 2 atmospheres by 700 millimeters of mercury per 1 atmosphere. And so in that case, we will get, again, choice B, which is 1520. So this slide here kind of shows how you would set that up. Here, we set up that conversion factor of 1 atmosphere per 760 millimeters of mercury. So we then, essentially are just dividing 475 by 760. In part B, we're using the same conversion factor, again, just flipped around. So here, we want to use 760 millimeters of mercury per 1 atmosphere, and then multiply that by 2 atmospheres. And we get that 1520 millimeters of mercury, which is choice B. So as described before, the unit atmosphere describes the atmospheric pressure, and it's the normal pressure that's exerted by a column of air from the top of the atmosphere to the surface of the earth. And so here is just showing a picture that if you are lower in elevation, you're going to have a higher pressure because you have more air on top of you. And so more air on top of you would be basically more pressure on you. But if you were at higher elevations, like at the top of a mountain, you have essentially less air on top of you. So you have less air pushing down on you, and so you have less pressure higher in elevations. The book goes into different properties and behaviors of gases because of those changes in pressure, but we're not going to go any more in detail than this. So atmospheric pressure is about 1 atmosphere at sea level, and so that's where that unit comes from. And so to give some other properties of atmospheric pressure here, but that is essentially the main one that you want to be aware of. What tool that we use to measure pressure is a barometer. A barometer measures the pressure exerted by gases in the atmosphere. And typically we use mercury in a barometer, and that's because mercury has a high density, and so we can use small amounts of mercury and small columns of mercury to measure the pressure. So you can see that in this picture that if we have basically a pool of mercury and then a column, a glass column, the pressure of the gas pushes down on that pool of mercury. And so then that allows that mercury to be pushed up in that glass column. And so that's how we measure the pressure using this barometer. And so the pressure is related to the height of that mercury in that column. And so at normal pressure, that height of that mercury would be 760 millimeters. And so that's where they get that conversion of atmospheres to millimeters of mercury. So we're not going to have to use a barometer or anything like that in the class, but you may come across that in your everyday lives, and essentially this is how it's done. So now we're getting into many of the gas laws and many of the calculations that are going to be pertaining to calculating the variables describing these gases in different situations. So the first law we're going to discuss is Boyle's law. And so Boyle's law relates volume and pressure of a gas. And so pressure is inversely related to volume. So that just means that when we have a higher pressure, we're going to have less volume. And when we have a lower pressure, we're going to have a higher volume. And so you can look at it in terms of this piston here. If we have, we'll look at the right hand picture first. If we squish down on a gas in a piston, we're squishing down, we're basically decreasing its volume. And so when we squish down on this gas, the gases have less room to move. And so the gases, they're moving at the same speed. They still have the same temperature. We still have the same amount of gas. So they just have less room to move. And so they're going to collide with the walls more often. And so we said before that pressure is related to the force of the gases. And so here they're going to be hitting the containers, the side walls of the container more. And so we're going to have more pressure. So when you squeeze down on it, you're basically giving the gas less room to move, and those gas molecules are going to hit the walls more, increasing the pressure. But then if you lift up that piston, they have more room to move, and so then they're going to be hitting the walls less frequently, and so there'll be less pressure because of that. And so you can see the different values underneath those pictures there. So Boyle's law states that the product of pressure times volume is constant as long as temperature and the amount of the gas does not change. So if we have two different scenarios, if we have the first scenario being having a pressure of 8 atmospheres and having a volume of 2 liters, that would give a product of 16 atmosphere liters. If we were to increase that volume to 4 liters, the pressure would adjust and decrease down to 4 atmospheres. But you can see that the product is still the same. It stays constant. And so we use Boyle's law by saying that in the first situation, P1V1, the first pressure and the first volume, is equal to the product of the second pressure and second volume. So P1V1 is equal to P2V2. You will not have to memorize that equation. That equation will be given to you. So you just want to make sure that you keep the different environments and different situations separate. So the first set of conditions you want to have on one side of the equation, and then the second set of variables on the right side of the equation. So we'll just go over how to use Boyle's law in solving for missing variables or predicted variables in different situations. And so what we want to first do is, as always, want to just organize our data and maybe set up a table of our initial and final conditions, our first situation and our second situations. And then we want to rearrange the gas law equation so we can solve for the unknown variable. And then the last thing we'll have to do once we set it up is just plug in the values and calculate the unknown variable. So here we have an example where we have a sample of nitrogen gas. It has a volume of 4.2 liters at 1 atmosphere. And it wants us to predict the new volume if we decrease the pressure to 0.75 atmospheres, as long as we don't change the temperature or the amount of gas. So using our facts that we know before, we know that the pressure is decreasing. So we should expect the volume to increase. So that can just serve as a check. So next thing we want to do is just write out our equation, P1V1 equals P2V2. And then since we are solving for the second volume, we want to divide both sides by P2. And when we do that, we get volume the volume that we're looking for, V2, is equal to P1 times V1 divided by P2. And so all that is left now is just plugging in our values. So our first volume was 4.2 liters. Our first pressure was 1 atmosphere. And then our second pressure was 0.75 atmospheres. So we're going to multiply 4.2 by 1 and then divide by 0.75. And we get a new volume of 5.6 liters. And so with that decreased pressure, we saw that the volume increased. So that does, at least our answer makes sense. And so we just want to double check and make sure your answers make sense in terms of the properties that you know. And so we can see Boyle's law in action in our everyday life just by breathing. And so when we inhale air, our lungs are going to expand. We're going to increase the volume in our lungs. And so because of that, the pressure in our lungs decreases. And so air is just naturally going to want to flow toward where there's less pressure to kind of balance it out. And so the air will then get into our lungs. Then our lungs are going to fill up with air. And so we're going to exhale. And when we exhale, we're decreasing the size of our lungs. And so when we decrease the volume in our lungs, that increases the pressure. So that pressure is basically going to force the air out. So here we'll go over another example where we have a CFC that we have mentioned earlier, a chlorofluorocarbon. And these things are bad for our environment because they destroy the ozone layer. And so in this question, it's asking us to solve for the new volume of an 8-liter sample of Freon after we change the pressure from 550 millimeters of mercury to 2200 millimeters of mercury. And it says that we're going to have a constant temperature and we have a constant amount, even though it's not stated, but that's we have to assume that. So we just first want to set up a table or set up and organize our data. We know both pressure conditions and we know the initial volume of our sample. And so we see that in the first condition, our first pressure compared to our second pressure, the pressure is increasing. So they have an inverse relationship. So we should expect that the volume is going to decrease. And so we first just write down our equation, P1V1 equals P2V2. And then we're going, since we're trying to solve for the second volume, we want to divide both sides by P2. And so when we do that, we get V2 is equal to V1 times P1 divided by P2. And so once we have that set up, then we can plug in our numbers and solve for our new volume. And so our first volume was 8 liters. Our first pressure was 550 millimeters of mercury. And our second volume was 2200 millimeters of mercury. So it becomes 8 times 550 divided by 2200. And we get a new volume of 2.0 liters. And so with the increased pressure, we expected a decrease in volume. And so we see that decrease from 8 to 2. So our answer makes sense in terms of that behavior of gas. So in this question, it's asking us to figure out what's the new pressures, if the pressure is going to increase or decrease for A and for B. So if we have, we see that where the piston is in the helium cylinder. And so in A, we see that we're squeezing down on that helium in that cylinder. And so we're decreasing the volume. And so we're squeezing that gas, giving it less volume. And so they have an inverse relationship. So if we decrease the volume, we should increase the pressure. So A would be matched up with letter B. And then in scenario B, we are giving the gas more room, and by giving it more volume, and so it has more volume, so the volume increase, and so it should have an opposite effect on pressure, so the pressure should decrease. So B should be matched up with letter A. And so that's what we see here. So now we'll be looking at the effects of temperature and volume and how they relate in terms of gases, and that's related by Charles's law. So Charles's law states that the temperature in units of Kelvin of a gas is directly related to the volume of the gas. So there's a direct relationship. So direct means if one goes up, the other goes up. One goes down, the other goes down. And this is true as long as we have pressure and the amount of gas constant. And so to put a real life scenario to this, if you leave a say a basketball outside on a cold day or a cold night, you know that when you go out the next morning, that ball is going to feel like it's lost air. But what's happened is just that with that cold temperature, the volume has decreased. The volume of that gas is decreased. And if you were to let it sit out during the day and let it heat up, that volume would then go back to normal, would go back and increase. And so, or sometimes in the winter, you have to make sure that that you have you want to check your tires, because with the colder temperatures, that cold air wants to contract and wants to get smaller. And so that just kind of puts a real life spin on what this law states. The equation that we used for Charles's law is V1 over T1 equals V2 over T2, with pressure and the amount of gas held constant. And so you won't be asked to memorize this equation either. This would be given to you. And so you just want to make sure that you put the correct variables in the correct place when you're solving problems that use Charles's law. And so here, just showing you a picture of this situation. And so here, if you have a lower temperature on the gases by putting a little bit of heat to them, you're going to have a smaller volume. But then if you increase that temperature by maybe increasing that flame, then you're going to give more energy to those gas molecules, and they're going to push out more and they're going to expand. And so you see that in the second picture, where the volume of that gas increases with the increase in temperature. So here we'll go over an example problem that uses Charles's law. And so it's given us a scenario in which we have a volume of 3.1 liters of neon gas that has a temperature of 12 degrees Celsius, and wants us to solve for the new volume of the gas if we're to increase the temperature to 32 degrees Celsius. And we have to assume that the pressure and the amount of gas is held constant. So it was stated earlier on in the lecture that if we were to have and solve for any properties of gases that involves temperature, we have to use the units of Kelvin for temperature. And so in our table here, it shows that conversion. And so in order to solve for and convert from degrees Celsius to Kelvin, we need to add 273. So in our first temperature from 12 degrees Celsius becomes 285 degrees Kelvin. And the temperature of 32 degrees Celsius becomes 305 Kelvin. And we can keep our volumes as liters. And we know that the temperature in this scenario increases, and temperature and volume have a direct relationship. So if we increase temperature, then we should expect an increase in volume. So our next step is we just want to write out Charles's law, which is V1 over T1 equals V2 over T2. And then we want to rearrange that equation to solve for V2. And so to do that, we're going to multiply both sides by T2. And so our equation becomes V2 is equal to V1 times T2 divided by T1. Our first volume was 3.1 liters. Our second temperature was 305 Kelvin. And our first temperature was 285 Kelvin. So we multiply 3.1 times 305 divided by 285, and we get a value of 3.3 liters. Here we'll have another example where we have a balloon that has a volume of 785 milliliters, and that's at 21 degrees Celsius. And so if we were to decrease the temperature to 0 degrees Celsius, what would be the new volume of the balloon, as long as we kept pressure constant? So as stated before, we have temperature in Celsius, so we need to convert that to Kelvin by adding 273. And it doesn't show that equation done out, but it shows you both temperatures. We also see that temperature decreased, and so the temperature and volume have a direct relationship. And so if we decrease temperature, we should expect a decrease in volume. So once we have our variables written out, we can write out our equation, V1 over T1 equals V2 over T2. And since we're solving for the new volume, we want to multiply both sides by T2 to get the same equation as we used before. V2 is equal to V1 times T2 over T1. And so then we multiply 785 by 273 and divide that by 285, and we get a new volume of 729 milliliters. And so it does not matter if we had liters or milliliters, they would have came up with the same answer. So we didn't have to do any type of conversion out of milliliters. So that's fine to do. The next gas law we look at is going to describe the relationship between temperature and pressure with Gay-Lussac's law. So Gay-Lussac's law states that pressure is directly related to the temperature in units of Kelvin, and as long as we keep volume and the number of moles constant. And so they have a direct relationship. So an increase in temperature should experience an increase in pressure, and vice versa. So we have the equation P1 over T1 equals P2 over V2. So here's an example using Gay-Lussac's law, in which we have a gas that has a pressure of 2.0 atmospheres at 18 degrees Celsius, and it's asking us to determine the new pressure when we change the pressure to 62 degrees Celsius. So again, it's giving us temperature in terms of Celsius, so we must convert to Kelvin. And so in order to do that, we must add 273 to our degrees Celsius. And so 18 degrees Celsius becomes 291 Kelvin, and 62 degrees Celsius becomes 335 Kelvin. And we can keep the units of atmospheres. And so Temperature and pressure have a direct relationship. So we see an increase in temperature, so we should expect an increase in pressure. So step 2 is just rearrange the equation. So we're going to write out an equation, P1 over T1 equals P2 over V2. And so since we are solving for our P2, then we want to multiply both sides by T2. And doing that, we get the new equation, P2 is equal to P1 times T2 over T1. And so then all we have left is plugging in the numbers and solving for our equation. And so our initial pressure was 2 atmospheres. Our final temperature was 335 Kelvin. And our initial temperature was 291 Kelvin. So it's 2 atmospheres times 335 Kelvin divided by 291 Kelvin, and we get a pressure of 2.3 atmospheres. So we saw an increase in temperature, and we predicted an increase in pressure, which we do see, and so our answer makes sense in terms of the expected behavior of the gas. We'll do another example in which we are asked to solve for the final pressure of the gas that has an initial pressure of 1.2 atmospheres at 75 degrees Celsius when it's cooled to negative 22 degrees Celsius. So again, here we have Celsius as our temperature, so we need to convert to Kelvin, so we need to add 273. So our T1 becomes 348 Kelvin, and our final temperature becomes 251 Kelvin. We want to write out the equation, P1 over T1 equals P2 over V2. And since we are trying to solve for the final pressure, we want to multiply both sides by the final temperature. And so in doing that, we get the equation P2 is equal to P1 times T2 over T1. And so then all is left is plugging it in and solving. And so our initial pressure was 1.2 atmospheres. Our final temperature was 251 Kelvin, and our initial temperature was 348 Kelvin. And that gives us so then we multiply 1.2 by 251 and divide it by 348, and we get a pressure of 0.866 atmospheres. The trickiest thing with these types of questions is making sure that you keep the initial conditions and the final conditions constant, and make sure you keep them in the right place. Make sure you relate them properly. So make sure that you read the question over a couple times and make sure that you have the correct numbers with the correct conditions. So make sure that you put the initial pressure and initial temperature as P1 and keep the final pressure and final temperature with P2, and just make sure you plug them in the right place. Those are that's pretty much the trickiest part, because the equation is going to be given to you, so you just need to make sure you put things in the right place, basically. You may have heard the term vapor pressure, and vapor pressure is just the pressure of the vapor or the gas above the liquid that you have in a container. And so the as temperature increases, you're going to have more vapor forming when it's being set out, and so vapor pressure increases. And so the one that's most commonly used is the vapor pressure of water. But we're not going to really use it too much in this class, but in case you hear of this term in the future, you know what it is. So vapor pressure is just the amount of pressure created by the gas created over the liquid that you have in a container. And so here, like I said, water is the most commonly used example, and this is mainly relevant when you talk about boiling liquids. And so, by definition, a liquid will boil when its vapor pressure becomes equal with the external pressure. And so, this is the reason to why um, uh, water and other gases or other liquids boil faster at lower temperatures at higher elevations, because there's less pressure up at higher elevations, and so you don't need as much vapor pressure from those from that liquid, and so it's easier to boils at lower temperatures. But we're not going to go into that too much, but you may experience that if you ever go hiking or something like that. So the next law we'll look at is the combined gas law, and this just combines all three of those laws we had just went over. So um, this relates pressure, temperature, and volume all together. And so the combined gas law combines um, those three laws as long as we keep N, or the amount of the gas, constant. And the equation that we use is P1 times V1 divided by T1 is equal to P2 times V2 over T2. So by using the combined gas law, you can derive any of the other gas laws, because if you use the combined gas law and any of those properties are held constant, they basically cancel out in the equation. So you can see that you can see how Boyle's law and Charles's law and Gay-Lussac's law can all be solved for by using the combined gas law. So if you know how to use the combined gas law, then you won't really even need to use Boyle's law, Charles' law, Gay-Lussac's law, because all the other variables will cancel out. So here we'll go over a couple examples, of course, by using the combined gas law. And so here we have a 0.180 liter sample of gas that has a pressure of 0.8 atmospheres and a temperature of 29 degrees Celsius. It's asking us the new temperature that the gas will have if we change the volume to 90 milliliters and the pressure to 3.2 atmospheres. So there's two things here. One, of course, we see temperature in terms of degrees Celsius, so we must convert that to degrees Kelvin. So we must add 273 to that. And then we must make sure that our volumes are in the same units. One volume we have in terms of liters, the other we have in terms of milliliters. So you can convert liters to milliliters or milliliters to liters, either way, but you need to have them in the same unit. So in here, we converted milliliters to liters. And so now, once we have all our variables set, so we know the initial conditions, we had 0.8 atmospheres, we had 0.18 liters of gas, and we have 302 Kelvin temperature. In the final conditions, we changed it to 3.2 atmospheres and 0.09 liters. Now we want to rearrange the gas law equation. So we want to first just write it out. P1 times V1 over T1 equals P2 times V2 over T2. We are solving for the final temperature, T2. So we want to basically cross multiply and divide a bunch of times and get T2 by itself. So what we can first do is multiply both sides by T2. Then we can divide both sides by P1 and V1. And then multiply both sides by T1. Sounds like a lot of work. It's not necessary to do if you don't want to. If you don't want to solve it in terms of the variables, then you can just plug in your numbers from the equation and then solve it that way. That would be fine. And we can go over examples of doing that in the example worked out example videos. But if you do solve it in terms of variables and you rearrange them, you would get T2 is equal to P2 times V2 times T1, I guess it got cut off, divided by P1 divided by V1. And so then you just plug in your numbers. Our final pressure was 3.2. Our final volume was 0.09 liters. And our initial temperature was 302 Kelvin. Our our initial pressure was 0.8 atmospheres, and our initial volume was 0.18 liters. So we multiply 3.2 by 0.09 by 302, then divide it by 0.8 and 0.180, and we get 604 Kelvin. And so then it asks specifically in this question, what would be the temperature in degrees Celsius? So to go from Kelvin to Celsius, you do the opposite and subtract 273, and you would get 331 degrees Celsius. So here we have another example in which we have a gas that has initial conditions of 675 milliliters and 35 degrees Celsius and 0.85 atmospheres. And it's asking us to solve for the new volume if we were to cool it down to negative 95 degrees Celsius and have a pressure of 802 millimeters of mercury. So here we have two sets of conversion we must perform before we solve for anything. The first of which we have two different units of pressure. We have atmospheres in the initial conditions and millimeters of mercury in the final conditions. So first off, we want to divide our 802 millimeters of mercury by 760 to solve for the pressure in terms of atmospheres, and we would get a pressure of 1.06 atmospheres. The second conversion is, of course, the temperature, and so we must add 273 to all of the temperatures to get and convert them to degrees Kelvin. And so we get the initial temperature at 308 Kelvin and the final temperature at 178 Kelvin. Then we can write out our combined gas law, P1V1 over T1 equals P2V2 over T2, and we can plug in our numbers from there and solve, or we can rearrange it, and if you rearrange it, you get V2 is equal to P1V1 T2 divided by T1 P2. And so plug in your numbers. The initial volume was 675. The initial pressure was 646. And the final temperature was 178 Kelvin. The initial temperature was 308 Kelvin. And the final pressure was 802 millimeters of mercury. So we multiply 675 by 646 by 178 and divided by 802 and 308, and you get a final volume of 314 milliliters. We're going to mention Avogadro's law, which relates volume in moles, and we do this so we can get to our final gas law. Our Avogadro's law basically relates the volume of gas to the number of moles of gas, and so they have a direct relationship, basically saying if you got more moles of gas, if you got more gas, you got more, it's going to take up more room. So there's a direct relationship as long as we keep temperature and pressure constant. And so the equation that's used is V1 over N1 equals V2 over N2. I didn't ask you to solve for any equations in your homework using this law. So we're not going to do any examples here, but we are going to state that for mainly for the reasoning for the next law we'll discuss. Some questions will make reference to STP. And so STP is standard temperature and pressure. So these are basically conditions that are most commonly used. So this is a normal normal conditions, 273 Kelvin, which is 0 degrees Celsius, so and standard pressure, just 1 atmosphere. So it's just arbitrary conditions that are used as a set of conditions to compare different gases under these conditions. And so if a problem states STP, you'll have to remember that that is at 273 Kelvin and 1 atmosphere. At STP, 1 mole of gas will always occupy 22.4 liters under STP. So no matter what gas you could have nitrogen, you could have oxygen, you could have helium. It doesn't matter the mass of the gas, but if you have 1 mole of these gases, they'll all occupy the same volume under STP. And we can see that in these balloons as an example. We have different masses of these gases, but they're under the same temperature and under the same pressure. And even though they have different masses, they have the same amounts in terms of moles. And so they occupy the same volume. They take up the same amount of space. And so we can use this conversion factor under STP, that 1 mole of gas occupies 22.4 liters. But the main reason for the mention of Avogadro's law was so we could relate moles to the behaviors and properties of gases. And so if we were to combine and look at all 4 of these properties at one time and combine them into a single equation, we would come up with this ideal gas law. The ideal gas law relates how gases behave and their properties under perfect conditions. And so the equation that's used to relate that is PV equals nRT. Pressure times volume is equal to moles times temperature times R, which is a constant. R we'll discuss in just a bit. If R is what we call the universal gas constant, and it is solved for, it's derived from dividing the pressure and volume by moles of gas and temperature. And it's a constant. No matter what conditions you have of these gases, you end up with this constant. And so you can solve for it under perfect conditions under STP. If you have STP is 1 atmosphere, and if you have 1 mole of gas, it occupies 22.4 liters at 273 Kelvin. And so if you plug in all those numbers, you get this universal gas constant, 0.0821 liters atmospheres per mole Kelvin. And this works for all gases. It doesn't matter what gas you have. As long as you have 1 mole at STP, you will end up with this, this gas constant. It doesn't even need to be at STP. You'll still get this gas constant, no matter what mole of what gas you have. That's why it's universal. And so this is a constant. You will now have to memorize this unit and the unit, the number and the units. This will be given to you, and you'll have to use it in calculations. And so we'll go over how to use it in the following slides. So one thing you want to pay special attention to with the universal gas constant R, or ideal gas constant R, is the units. You want to look at it and see that for the 0.0821 constant, the one that we're going to use, a lot more than we'll use the one in the last column. You want to look at the unit pressure is in atmospheres, the volume is in liters, the amount is in moles, and the temperature is in Kelvin. And so you want to make sure that when you when you have to solve questions and problems using the ideal gas law, you want to make sure that your pressure that you plug in is in atmospheres. You want to make sure your volume is in terms of liters. You want to make sure that your amount is and your N is in terms of moles, and your temperature is in Kelvin, so that your units um, will be able to cancel out. So this kind of little flow chart to explain how you'll be solving questions that are use the ideal gas law. You want to, one, just state everything that you're given. What variables do you have? What are their values? What are their units? You may have to convert some things if you need to. Then you want to write out the the ideal gas law and rearrange it to solve for the variable that you're interested in, and then plug in your numbers and solve. So here we have an example where we have dinitrogen oxide, which is laughing gas, and it says that if we have a 20-liter tank of laughing gas and it has 2.86 moles and it has 23, it's at 23 degrees Celsius, what would be the pressure of that gas in the tank? So the first step is just to, you want to make sure you just write out everything that you're given. It gives you the volume of 20 liters. It gives you the number of moles of 2.86. It gives you the temperature of 23 degrees Celsius, so you need to add 273 to convert it to Kelvin. And this question is asking for the pressure in millimeters of mercury. And so because of that, you're going to use the gas constant that has the units millimeters of mercury, even though ones that I'm going to give you on the quiz and probably on the final, you'll use the other gas constant, but it's done in the same way. And so when I make the video of working out problems, we'll probably use the other gas constant. But like I said, it's still used in the same way. So the main thing you want to do is just look at the units that you're given. All right, and so here it's asking for pressure, and it was looking for the pressure in millimeters of mercury, and so that's why we're using that second value of the gas constant R. So we start off by writing out the equation PV equals nRT, and since we're looking for pressure, we want to get pressure by itself, so we divide both sides by V, and so we get P, pressure, is equal to N times R times T over V. Our moles is 2.86, our N. Our R, we're going to use 62.4. Our temperature, T, is 296. And our volume, V, is 20 liters. And so when you'll multiply 2.86 by 62.4 by 296, and then divide that by 20, and you get 2.64 times 10 to the third millimeters of mercury. We can also use the ideal gas law to solve for the molar mass of a gas. And so it's done in the same way, except that once you basically solve it to figure out the number of moles in your situation, and then use the mass by and the moles that you solve for, and divide mass by moles to figure out the molar mass. And we'll show an example in this next coming slide. So here it says that we have a cylinder of that's 5 liters of an unknown gas at 20 degrees Celsius at 0.85 atmospheres. It's asking us to solve for the molar mass if we have 5.8 grams of this gas in the cylinder. So we just want to first write out our variables. We know the pressure is 0.85 atmospheres. We know that the volume is 5 liters. We know that the gas constant, since our pressure is in atmospheres, now we're going to use the R, that's 0.0821 liters per atmosphere per mole Kelvin. So you basically determine what R you're going to use by what pressure you have. And then our temperature is 293 Kelvin, and that's just by adding 20 and 273. And we're looking for the number of moles. So we know the mass, but in order to get the molar mass, we need to figure out the number of moles in this situation, because molar mass is grams per mole. We know the grams, we don't know the moles. So first we need to solve for moles, and then we can get grams per mole. So we start off with PV equals nRT, and because we know we're looking for N, then our equation becomes N is equal to PV divided by RT. Our pressure is 0.85 atmospheres. Our volume is 5 liters. Our R is 0.0821. And our temperature is 293 Kelvin. And so then we solve it by multiplying 0.85 by 5, dividing it by 0.0821 and 293, and we get 0.18 moles of gas. Now we have mass and we have moles. Molar mass is mass divided by moles. So we know our mass is 5.8 grams from our question, what was given to us. And we know now that we had 0.18 moles of gas. So we divide 5.8 by 0.18, and we get 32 grams per mole. And that would be oxygen, O2 gas. And now the last thing we'll look at is partial pressures, which is Dalton's law. And so we'll look at what Dalton's law is in this next and last section. So most often we have mixture of gases, and each gas exerts its own pressure, and we call that their partial pressure. And so Dalton's law states that if we were to add all the partial pressures, or the pressures of each gas, they would add up to the total pressure that you experience of all the gases. So basically, if we had a tank of helium at 2 atmospheres, and we had a tank of argon at 4 atmospheres, if we were to put all of those gases in one container of that same size, you would have a total pressure of 6 atmospheres. So the pressures add together. At STP, if 1 mole of pure gas would exert the same pressure as 1 mole of combined gases. So it doesn't matter if you have a mixture of different gases or just one pure gas. If they're the same total number of moles, you're going to have the same total pressure. And so you see that in these scenarios. All right, so if we have 1 mole of nitrogen gas, it's going to exert a pressure of 1 atmosphere. If we were to have 0.4 moles of oxygen and 0.6 moles of helium, it still combines to 1 mole of gas, and so it still have a pressure of 1 atmosphere. And the same thing with the last scenario with the 3 different gases. So here just shows the composition or the makeup of the air that we breathe in every day. The air that we breathe in is mostly nitrogen. You can see in the chart, it's almost 80% nitrogen. We have a good bit of oxygen. We have a little over 20% of oxygen. And then very little of everything else. Less than 1% of carbon dioxide, argon, water, and minimal amounts of everything else. But you can see that we know that normal atmospheric pressure at sea level is 1 atmosphere, or 760 millimeters of mercury. So if we were to add all the pressures, the partial pressures of each of those gases together, they add up to 760 millimeters of mercury. And so, those partial pressures add up to the total pressure. So we'll go over a couple examples of solving partial pressures. And so what we first want to do is just write out the equation of our partial pressures. We want to rearrange the equation to solve for our unknowns and then plug in everything that we know and calculate the unknown. So here we are looking at a scenario where we have a scuba tank that contains a mixture of helium and oxygen, and it's at a pressure of 7 atmospheres. If we know the pressure of oxygen is 1,140 millimeters of mercury, it's asking for what is the partial pressure of helium in the tank. So we first want to write out our equation. The total pressure is equal to the pressure of oxygen plus the pressure of helium. Since we're looking for the partial pressure of helium, that will equal the total pressure minus the partial pressure of oxygen. Before we start solving for it, we see that we have two different units of pressure. We have our total pressure in atmospheres, our partial pressure of oxygen in millimeters of mercury. So we want to convert our millimeters of mercury to atmospheres. And so we use our conversion factor of 1 atmosphere is equal to 760 millimeters of mercury. So essentially we divide 1140 by 760 and we get a partial pressure of oxygen gas of 1.5 atmospheres. And so now the last thing we have to do is just do a simple subtraction. So the partial pressure of helium is equal to the total pressure, which is 7, minus the partial pressure of oxygen, which is 1.5 atmospheres, and we get a partial pressure of helium to be 5.50 atmospheres. So to relate partial pressures to biology, we can look at how oxygen and carbon dioxide flow in our respiratory and cardiovascular system here. And so in our lungs we have oxygen entering the blood, and at the same time we have carbon dioxide being released from the heart. And in our tissues we have oxygen entering the cells in our tissues, and we have carbon dioxide being released into our blood, going back and trying to be pumped out. So you kind of see how it's flowing in and out. Right? We're trying to get oxygen to flow in, and we're pushing out the carbon dioxide through respiration. And so the main reason that the oxygen flows is because looking at that picture, you see that there's a higher partial pressure of oxygen in the blood than in the tissues. So it wants to balance out. It wants to go to where oxygen is needed. It wants to go from high pressure to low pressure. It wants to balance out in that way. And same thing with the carbon dioxide. The carbon dioxide was higher partial pressure in the cells of the tissues and lower in the lungs. So it wants to balance out by going out toward the lungs. And so that's how most things work. They want to go from areas where there's a lot of it to where there's not a lot of it. And so there's more oxygen in the lungs than in the tissues. So it's going to flow, the oxygen is going to flow toward the tissues. There's more carbon dioxide in the tissues than in the lungs. So the carbon dioxide is going to want to flow toward the lungs. And so here, you can just see the differences in the partial pressures of all the different gases throughout, the in the air that's both intake and expired after it leaves our body. So you can see that when we take in air, there's a very little concentration of carbon dioxide or partial pressure of carbon dioxide, and a large amount of oxygen. And then on the way out, we can see that partial pressure of carbon dioxide is a lot higher, and the oxygen has decreased. And so we're using that oxygen, and when we're exhaling our carbon dioxide. And so we just look at the partial pressures and see how the partial pressures flow from areas of high concentration to low concentration. And so that's what makes the system work. And so that concludes our look at gases, their properties, and their behaviors and their laws. There's lots of laws, and calculations, but you don't need to memorize any of these equations or constants. You just need to know how to use them. You need to make sure you know how to, and make sure that you relate the initial conditions and the final conditions properly. Make sure you put your variables in the right place, and solve. So we'll go out, post a video of the examples, working through examples, and show the process that I kind of worked through in solving for these unknown variables in different situations and different conditions. So, and that concludes this presentation.